Hello everyone. I'm really happy that we are together today to basically celebrate lots of really interesting and exciting findings in the field of brain stimulation for addiction medicine. And this panel is being organized by neuroscience interest group at International Society for Addiction Medicine. I'm really happy that we have this opportunity to present recent findings that we have in the field and kind of give clinicians from the addiction medicine side an idea about the potentials that we are expecting to have for brain stimulation in the field of addiction medicine. I do not have any conflict of interest, and different speakers today discussed about different potentials for different non-invasive brain stimulation technologies, and let me just see if I can use my pen. Okay. So as you kind of heard from different speakers, Bhumi talked about deep TMS devices, and Colleen was talking about conventional TMS devices, and Shirley was talking about TES and TDCS and TACS, and Tifei was talking about TMS and things that he's doing in China. So you can see people are using different technologies. What I'm going to give you some kind of new evidence from my lab is basically about what we call TES, or transcranial electrical stimulation, with direct current or alternating current or random noise stimulation. The reason I really like the transcranial electrical stimulation is that the technology is really scalable. So we could have devices with the price of something like a couple of $100s, and it could be something that people can use in the middle of the night. So it is far easier to implement compared to more expensive technologies like TMS. You probably need to pay at least a couple of $10,000 for the device. There are definitely pros and cons for this level of scalability, but that's the reason I really like that. And as Shirley has mentioned, there are different studies published by different groups, including the things that we have published in the field, that we probably can modulate drug craving using transcranial electrical stimulation. This is the study that we have done using putting the right anodal electrode on the right DLPFC and left cathodal on the left DLPFC. And as you can see here, we showed that without any kind of extra stimulation, we can reduce the level of craving with doing the stimulation with this specific montage. And then we showed that there would be a little bit of a complexity if we expose people to drug-related cues in terms of the response, but we still can show that there is a level of modulation with transcranial electrical stimulation and among drug users. And as Shirley has mentioned, there are systematic reviews showing that we probably can modulate drug craving, but meanwhile there are negative findings in the field as well. And if I even kind of want to show you the response among different subjects in terms of the TDCS effect in our trials, you can see that there is a significant level of variation in terms of the changes in the level of craving. And there is always a question why people are responding so differently to this technology. And we try to look into the potential variations and why we have different responses, and to be able to have a better idea about what is really happening inside the brain during the stimulation, we have started to basically combine transcranial electrical stimulation to brain imaging technologies. And we have done a study, it was one of the first studies in the field, doing brain stimulation and doing fMRI before and after to see what is the effect of TDCS, and we do fMRI pre and post. And with fMRI, we have been doing both resting scan and also a drug cue reactivity scan. So that is the crossover design of this study with the same montage that I told you in terms of the right anodal and left cathodal. And with anodal, we are kind of expecting to have a level of increase in excitability, and with cathodal, most of the time we are hopeful to be able to have a kind of a reduction in the level of excitability under the cathodal electrode. And one of the first questions that we had was, is there any chance that we can change the resting state large scale networks by just doing the modulation over DLPFC? And what we found, basically, the idea of we have three networks that are interacting to each other, basically default mode network, executive control network, and then saliency network, which is modulating between these two networks. We showed that there are initial results that probably TDCS might be able to modulate this interaction between these two networks toward having more activation in executive control network and also saliency network and the interaction between these two networks. That is the initial result that we showed. So it seems that we might be able to modulate large scale resting state connectivities. Meanwhile, we have been thinking about, okay, what will be the next step? People are exploring these ideas of, okay, we might be able to modulate executive control network in other psychiatric disorders as well, including depression. I'm sure you have seen this paper from Amit Etkin team in Stanford and his students in terms of the potential mechanisms of TMS for depression. And their idea is we are basically modulating executive control network in DLPFC and parietal cortex. And then when we modulate this executive control network connectivity, we are getting able to basically modulate the other networks that are connected to these networks. And this is the way that we do a top-down regulation as well. So that was the question that we explored in our database as well, how much we are able to modulate top-down regulation and how we might be able to change the connection between the site of the electrode and subcortical areas. What we found when we have been putting our seed electrode, seed ROI under the anodal electrode, which is basically stimulating the brain, we saw that we can have an increased level of connection to the insular cortex. My pen is not working really well, but it is connected to the anterior insular cortex. That the connection would be decreasing with the real stimulation compared to sham, and also there would be a significant level of change in connection to basically dorsal anterior cingulate cortex. So it seems that we are able to modulate these two nodes with the anodal stimulation. And if we put the electrode, the ROI under the left cathodal, that we are expecting to have a decreased level of excitation, it's quite interesting that we have sort of opposite effect in a bilateral way, that we have decreased level of task-based connectivity with anterior insular cortex. So that these are the initial findings that we have. So it seems that we are able to modulate things that are related to, let's say, mainly saliency network and changing the connection to what we call insular cortex and dorsal anterior cingulate cortex through the process of DLPFC. So that is the idea that seems that is working in this direction. But the idea is, okay, if we are able to modulate this network, let's try to modulate the executive control network in terms of DLPFC and posterior parietal cortex. And this is the justification for running another trial targeting these two nodes, basically DLPFC and posterior parietal cortex. So we started a trial with a specific protocol that we call frontoparietal synchronization, trying to do alternative current stimulation in both nodes, trying to synchronize two nodes on the executive control network to see how we might be able to modulate. And we already have an ongoing trial for this specific sort of technology with opioid users. But in the process of kind of doing initial analysis for the baseline data and some other explorations that we are doing with posterior parietal cortex and DLPFC connections, we have started to kind of do some analysis on the head models that we have, seeing, okay, if we are tapping into, let's say, executive control network and then the posterior parietal cortex in the executive control network, how this system is working. So we have done some modeling analysis with one of my PhD students, Khazale, with these two basically nodes. But what we realized that basically F4 and P4 and F3 and P3 are not connected, and basically they are not, they do not have any task related connectivity. And that was pretty much frustrating because we have been expecting that these networks are involved in, because this is the task-based connectivity during drug Q exposure. So we have been expecting to have this task-based connectivity in frontoparietal areas, but it seems that the task-based connectivity is not there. And that was pretty much frustrating, especially as we are in the middle of running a trial, trying to tap into these areas. So we started to think about, okay, if we put the kind of the seed on those areas that we have been exploring, what could be the whole brain task-based connectivity? What are the areas that are connected to, let's say, F3 and F4? And we realized that when we put the electrodes on the, let's say, right side, or we put it on the left side, we always have a large cluster in the whole brain analysis. The largest cluster would be a cluster in parietal cortex. So we have a cluster in parietal cortex. But it seems that this cluster is not under basically P4 or P3. So we put those clusters over the cortex and try to see what could be the electrode that would be targeting that node on the parietal cortex, and we realized that could be CP5 and CP6. So we have done our analysis again, and this is basically the result. So when we do the analysis again with two new nodes in the parietal cortex, we realize that, okay, it seems that things would get connected in a significant way between frontoparietal. But I mean, as you can see here, we do not have it F3, F4, P4, and F4, P4, but we have connection with other nodes. So it seems that we have the connection in the parietal cortex, but it was not the network that we have been exploring before. And we have done that with resting state fMRI as well, and it is the same for resting as well. So it seems that with resting, we do not have connection, and we even have sometimes negative connection between F3 and P3, but we have significantly positive correlation between F3 and CP5. And in this process, we have to start thinking about, okay, why we have this, let's say, a level of confusion compared to what we have been expecting before. If you take a look in the Yo atlas in terms of the major networks, we have been thinking about, okay, this is the executive control network, and this is basically the parietal side. You can see that there is basically a cluster here in the prefrontal cortex, which is the area that we are tapping into in the stimulation that we are doing. And this cluster is not a part of the frontoparietal network. It is a part of a network that they call, I'm not sure if people can remember the name of this network. It is called the ventral attentional network. And this network is also connected to insular cortex, and it is connected to a part of parietal cortex which is a little bit down to the P4 area. It's basically exactly the area that we have been discussing about that would be connected to. And there are also connections with the, let's say, dorsal anterior cingulate cortex part. So we have done some analysis in terms of if our nodes are connected to insular cortex. It seems that our nodes are connected to the anterior insular cortex. And also in terms of the ACC, we are connected to the dorsal ACC as well. So these are basically those nodes that we have been seeing before in terms of the connection between frontal areas and cingulate cortex and insular cortex. So it seems that we are tapping into another network, not the frontoparietal that we have been thinking, but another ventral attentional network, which is quite interesting. And we have explored in terms of the frontoparietal connectivity, frontolimbic connectivity and top-down regulation. And we realized that this network is also connected to the subcortical areas, and the connection between frontal areas and those subcortical areas would be highly correlated to some of the activations that are related to drug craving. So it seems that this is the network that we are tapping into. And those who are thinking about the frontoparietal, we might even need to start to think about, okay, are we really targeting the frontoparietal, or it is another, let's say, fronto, um, basically anterior attentional network, which includes insula and anterior cingulate cortex as a part of that network. So that is something that we probably can explore together in the future, being able to explore these sort of potentials. We have organized a new setup in our lab, being able to do imaging during the stimulation inside the scanner with multiple electrodes. This is the new setup that we started, of course, with watermelons and doing the test with that. And then, of course, the next subject after watermelon would be me. So we have been doing that over my head. And this is the setup that we have been successful in terms of putting electrodes. And even we had issues in terms of putting the electrodes not on the back of the head because the subject would be inside the scanner. That would be hard. So we have been successful in solving those challenges. And this is the setup that we have in terms of being able to control the stimulation during the imaging, and we have sort of a full control on that. Now the setup that we have, we are able to do the stimulation, record the, let's say, frontoparietal connectivity, and optimize the stimulation based on the frontoparietal connectivity that we are measuring. So that is this new setting that we are already, I mean, today we have a kind of something like I think he's going to be our 15th subject for this new ongoing trial that we have with this new setting that we put together. And at least technically it works really well. So I hope that the result would be good. Just something like the last 1 minute of the talk, just some other kind of ideas about what we might be able to do. The reality is those who are doing the brain stimulation studies in drug addiction, they are from different countries. And even the composition of speakers that you can see in this panel is an interesting combination of people from US, from China, from Canada. I have an Iranian background. So we are from different parts of the world. And we realize that we can work together and collaborate together. So with Colleen as co-chair, we have started to develop a network which we call International Network of TMS Trials for Addiction Medicine, and all the other speakers are basically champions of that network. And we put together a roadmap for what people can do in the future in this field. And I highly recommend people who are interested to have a kind of an idea about what they can do for the next step. Just take a look inside this consensus paper. And there are some other, let's say, okay, it seems that there is a problem in my slide. It was just something like the last 2-3 slides. There are also some other networks in terms of being able to do, okay, let's just, some other networks in terms of being able to do TES fMRI together, and we are happy to share our current experiences in being able to do concurrent TES fMRI or closed loop TES fMRI. And we have recently put together a sort of a technical note for that, and we will be happy to share with others. There are lots of, let's say, great potentials in the field for exploration. There are definitely lots of dead ends, and there are kind of lots of challenges to solve. We definitely need to have better biomarkers for brain stimulation trials. And we definitely need to have collaborative networks of people who work together. And I need to thank my colleagues, collaborators, and students, and those who helped us to be able to run these studies. Thank you very much for your attention.